Okay, so we are on lecture 8.1, gradient descent. Consider a multivariate function f that maps Rn to R. It represents some cost or value, okay? So, pretty broad, okay? It's pretty common to have a function that's going to represent those things. You can imagine that there might be a lot of variables of interest for a given application. You might want to be optimizing over several variables, but they affect each other, and they affect this one function. And you could add weights for different variables. You could say, okay, this variable matters more to me than that variable, and you could write one function that kind of combines all of these different variables and gives you some sort of function that you might want to maximize or minimize, okay? This is called an objective function. We often want to find x that yields f's extremum, minimum or maximum, depending on whichever is desirable, okay? It is important to note, however, that some functions have no finite extremum. Other functions have multiple. Finding a global extremum is generally difficult. However, many good methods exist for finding a local extremum, an extremum for some region in Rn. So, no method will guarantee that you'll get the global extremum in this function, but a lot of methods will yield a local extremum, and that's usually a pretty good start. You could go searching for others too if you wanted. The method explored here is called gradient descent. It will soon become apparent why it has this name. First, let's look at stationary points. Recall from basic calculus that a function f of a single variable had potential local extrema where the derivative of f is 0. The multivariate version of this, for multivariate function f, is the gradient of f is the 0 vector. A value x for which equation 8.1 holds is called a stationary point. However, as in the univariate case, a stationary point may not be a local extremum. In these cases, it is called a saddle point. Okay, remember the good old inflection point that we would get with x cubed? It has a derivative equal to 0 at 0, but it's not a maximum or a minimum. Consider the Hessian matrix H with values for independent variables xi, the partials of f with respect to xi and xj. Okay, so it's a matrix made up of these partial derivatives. It's called the Hessian matrix. For a stationary point x, the second partial derivative test tells us if it is a local maximum, local minimum, or saddle point. Minimum. If h of x is a positive definite, or is positive definite, so it's a positive definite matrix, all its eigenvalues are positive is an equivalent statement to all the, or for the matrix being positive definite, then x is a local minimum. Okay. This is like when we looked at the second derivative of a univariate function and we found that it was positive, and we said, oh, it's concave up there, we would say. Or maybe we said it's convex, which means it's shaped like x squared in that region, and that means that the extremum is associated with a minimum. Maximum. If h of x is negative definite, in other words, all its eigenvalues are negative, x is a local maximum. Okay? And saddle. So if h of x is indefinite, which means it has both positive and negative eigenvalues, x is a saddle point. These are sometimes called tests for concavity. Minima occur where f is convex, and maxima where f is concave. In other words, where negative f is convex. Should be another parenthesis there. It turns out, however, that solving equation 8.1 directly, so that's the grad f equals 0, for stationary points is generally hard. Okay, so especially when you have a lot of variables, when they enter the function nonlinearly, it's generally difficult to solve for those values analytically. Therefore, we will typically use an iterative technique for estimating them. The gradient points the way. Although equation 8.1, grad f equals 0, isn't usually directly useful for computing stationary points, it suggests iterative techniques that are. Several techniques rely on the insight that the gradient points towards stationary points. Okay? Recall from section 5.3, lecture 5.3, that grad f is a vector field that points in the direction of greatest increase in f. Consider starting at some point x naught and wanting to move iteratively closer to a stationary point. So if one is seeking a maximum of f, then choose x1 to be in the direction of grad f. If one is seeking a minimum of f, then choose x1 to be opposite the direction of grad f. The question becomes, how far alpha should we go in or opposite the direction of the gradient? Okay, you can move a little bit in the direction of the gradient, you can move a lot in the direction of the gradient. So how far should you move? Surely too small alpha will require more iteration, and too large alpha, that was just a typo, will lead to poor convergence or missing minima altogether. You could just skip right over them, right? This framing of the problem is called line search. There are a few common methods for choosing alpha, which is called the step size, some more computationally efficient than others. Two methods for choosing the step size are described below. The classical method. Classical method of choosing alpha is to attempt to solve analytically for alpha sub k, so the step at the step size at the kth iteration. You find the argmin over alpha of the function f evaluated at xk, so the current best estimate of a local extremum, a local minimum, minus alpha, the step size, times gk. I forgot to say that g sub k is equal to grad f evaluated at x equal xk. So you have to decide. So what you're doing is you're saying, okay, if you use a sort of linear projection of your motion here, so you're going to move in the direction gk, scale that by alpha, so how far you're going to go in that direction. And if you do that, then, and you're going to go against the gradient, you're going to use the minus sign to go against the gradient because we're going to do a minimization process. You can just flip this around, and it would be a maximization process. So you would add alpha times the gradient instead of subtracting. The solution approximates the function f as 1 varies alpha. So you turn this function f, which is a function of several variables, and you turn it into a variable of one function alpha. Argmin is looking for the minimum value of alpha, so it's going to return the minimum value of alpha for this function being minimized. Okay. It is approximate because as alpha varies, so should x, technically. So you're going to follow alpha along the line in Rn. Well, technically, the x's are changing too there, right? So it's really, I mean, if you had a parameterization of x in terms of alpha, if you could write such a thing, then it would be exact, and you would be able to follow it and find its minimum, this sort of section of your surface, the minimum there. But that would be, once again, very difficult to do. So we simplify by saying, okay, just alpha varies. Can you minimize over that? But even with alpha as the one variable, equation 8.3 may be difficult or impossible to solve. Okay? However, this is sometimes called the optimal choice for alpha. Okay? Here, optimality refers not to practicality, but to ideality. This method is rarely used to solve practical problems due to the difficulty in solving that for alpha. The algorithm for the classical gradient descent method can be summarized in the pseudocode of algorithm 1. It is described further in Kreisig, section 22.1. They do a good job with it, but it's just the classical method. So this is the algorithm. Okay, so while delta x, which is going to be, we're later going to say, okay, it's the difference of our estimate of a minimum for the next step minus the current step. So we're going to say, okay, how close are we to sort of converging on some point? Okay, if our x estimate isn't changing very much, we'll stop. So we'll set it up with the function, some initial value of our guess for a minimum, and a threshold to stop once it starts to not change very much, its estimate. So while that's true, while we haven't reached our threshold, we calculate the gradient at our current value, our current best estimate. We take alpha k to be argmin over alpha, so that's the same formula from above. And then we compute what the next estimate of x should be from that. And then we check to see, using the norm, that's the distance between the Cartesian distance between them, how close we are, or how close we are to converging. And then we add 1 to our iterator, our index, and we just keep going around. Once we've reached our threshold, then we return the current estimate of x. So that's the classical gradient descent method. Okay, so limited though, mostly in this our ability to calculate alpha k. Okay, so imagine, for instance, that you have if f is a, say, fourth order polynomial, fifth order polynomial, then alpha will enter into that polynomial with that same order, right? It'll end up being a fifth order polynomial in alpha, and you got to solve for alpha. Well, you're going to have 5 solutions, right? If it's fifth order, and you have to figure out which is the best one, first of all, and even getting that solution. I mean, in a polynomial case, up to fourth order, I think, is analytically solvable, but beyond that, you can get a numerical estimate then you're just doing a root solver for it, which is fine. But it's not great even for polynomials. If you start to put any other type of functions in there, it gets very messy or intractable. So we like the idea here, but in practice it's challenging. So there are certain types of functions for which you can solve this, but it's almost never used as a technique. Okay. Great. So in practice, several non-classical methods are used for choosing step size alpha. Most of these construct criteria for step sizes that are too small and too large and prescribe choosing some alpha that, at least in certain cases, must be in the sweet spot in between the too small and the too large. Barzilai and Borwein in 1988 developed such a prescription, which we now present. There's a reference to the paper. You can see the paper. It's a pretty nice paper. Let delta xk be the current xk estimate, or current estimate of an extremum, or of a stationary point at least, minus the previous one, and delta gk be the current gradient minus the previous gradient. This method minimizes the squared norm of delta x minus alpha delta g by choosing alpha k to be the dot product of delta xk dot delta gk divided by delta gk dot delta gk. The algorithm of this gradient descent method can be summarized in the pseudocode of algorithm 2. It is described further in Barzilai and Borwein. So the Barzilai minimizer, similar, okay, while we haven't got to the threshold yet, compute the gradient at the current value of xk, calculate your deltas from the previous gradient and previous x, take the dot products, divide them, update your xk. Okay, so update your xk, check to see if your x's are really close to each other, and iterate. So this alpha k is much better. It's much easier to compute than the classical alpha. Okay, it's pretty easy to compute. Okay, so let's do an example using the Barzilai and Borwein gradient descent. So consider the functions for part A, f1, and for part B, f2, defined as f1 is this quadratic here, so quadratic in x1 and x2. Then this is also a quadratic formula, and it's set up in a linear algebra way. And this is a classic form of our function that we'd like to minimize. And it arises when we're trying to solve linear systems, for instance. And there's a lot in the literature that uses this form. So I wanted you guys to be subjected to this form of the objective function, okay? Where I choose A to be this and B to be that. So we're working with once again, a function on R2 in both cases, starting at some initial value for our search, and then find a minimum of each function. Okay. I bopped outside the box of the example because I was having some issues and I don't really know what they were from, but hopefully later this will all be inside the box. Okay, so we'll use SymPy and NumPy and Matplotlib to do this. There's going to be some nice printing using tabulate. That's why I use that. So we begin by writing a class gradient descent min to perform the gradient descent. This is not optimized for speed. This is optimized for me getting this written starting at 10 p.m. last night. No, it was earlier than that. So we start out with some nice look at this. It's still documented code, not completely undocumented code. We're going to give it f, a Python function of x variables, x, a list of SymPy symbolic variables, for example, x1, x2, x0, a list of numeric initial guesses of a minimum of f, t, step size, threshold for stopping the descent. To execute the gradient descent, call the descend method. Okay, so we initialize it, and most of this is pretty straightforward. It says, okay, we'll put in a parameter of this class instance, and it'll be f. We turn x, this x, it could come in as a list, and so I want to turn it into a SymPy array object. X0 is going to come in as a list, and I want it to be a NumPy numerical array. The threshold is there. I'm going to have this internal parameter n, which is going to be the length of x, which is the number of variables that we're optimizing over, number of variables the function has. And g is going to be where we store our gradient expression. What I do here is I don't want to compute the gradient. So they're going to give us a symbolic, they're going to give us an f that's going to have symbolic variables in it. We need to compute the gradient of f. And computing the gradient of f is something that we don't want to do every time symbolically that we need to call it. So what I do is I write this little grad function here, grad method. And what it does is it takes in a function and x, and it uses the SymPy method derive by array. You give it the function of x, and you give it x, and what it does is it gives you essentially the gradient. But you have to be a little bit careful with this because you are, I didn't worry about coordinate systems here. We're going to assume we're going to be using Cartesian coordinates. If you're not using Cartesian coordinates, you have to worry about how to compute the gradient. So, okay, great. So what I do then is I compute the gradient symbolically down in that function. So I call that grad function when I initialize g, and then I lambdify it, which is to say I make it so that it can be numerically evaluated much faster than if you just plugged in numbers into the symbolic expression, which is not a great thing to do. So, and you don't have to recompute the gradient each time either. So it's kind of nice to do it that way. And then I initialize my xk, which is going to be, I'm going to keep track of the xk's just for plotting purposes. This is very inefficient. You don't want to keep track of all your xk's in a typical numerical method. You don't want to keep track of every step. It's just going to take a lot of memory. So for demonstration purposes, I'm going to keep track of it. I'll initialize it to the initial guess, and we'll go from there. And the only other thing here is the descend method. So just for ease of reading it, I unpack the variables f, x, x naught, t, and g, so that I don't have to call self.g every time I want to use g, etc. Initialize variables. N is going to be the step that I'm at, the iteration that I'm on. Xk, I'll start it off at x naught. Dx, I just called it 2 times t. Dx is going to be the threshold checker, right? And I don't want to initialize it so it's going to immediately stop it. Oh, little typo here. I meant to put this in there. Okay, so can't be 0. You just need to make it so that it's not going to be something that will stop the algorithm immediately. XKM1, which is the XK minus 1. So I have to initialize it to some initial value. I don't want to initialize it to x naught, because if I initialize it to x naught, then the first time through, my check is going to say, oh, your x estimate is exactly the same as your previous x estimate, and it'll stop the algorithm. So once again, it was just, you just sort of hack it so that it doesn't stop on the first one. I just bumped it a little bit. I made a little offset here in case x naught is 0. So that I did 0.9 times it, but then if x naught was 0, then they're still going to be the same. So I put a little offset there. NumPy array. So this G returns something that is a list, and I wanted it to be a NumPy array. So I do that. This is sometimes called the splat operator, which takes an array and it gives G, the function G, each of the values of the array as arguments instead of as an array. So G needed both arguments, not just an array. Can somebody ask it when their class is going to be? Thank you. We can finish up here. It's not going to be too much longer, but great. So what we do there is what was that? It's F5. Oh, they're just. Oh, Akara got locked out. So we're gonna have to do so max iterations. I want to have a max iteration. So I didn't want it to run forever if it wasn't converging. So I said 100, and then I forgot to plug it in here, and I had 10 in there. It always converged in less than 10 when I was doing it, so it's pretty nice. And then table data. Once again, I'm going to be doing some printing, so I'm like accumulating data. It's terrible. It'll fill up your memory really fast if you do that. So what I do is inside the loop, I find GK. So I compute the gradient using our G function here. And I subtract the old G, K minus 1G, and I get my dg, my delta g. I get my delta xk by subtracting the previous xk estimate. And then alpha k, according to this algorithm, is the dot product of dxk with dgk divided by the dot product of dgk and dgk. So that's what this line is. And then I store the old xk as xk minus 1. I compute the new xk. And that gives me this. That's this expression here. And then I store the old gk. And I increment my counter. And then I check to see if we have converged yet. And then this is for plotting purposes. I'm saving the xk data in a parameter of the method instance, class instance. And then I tabulate the data, and then at the end I'm going to print the data. And that's what I do, well, actually, so that was just the method. First, let's consider f1. So say we have variables x1, x2. X is an array, a SymPy array of x1 and x2. Then I have to define f1. I just use a lambda function to do that. So we give it some x, take the first element of it, subtract 25 squared, so that's the x1 squared. And then this is the x2 squared. Yeah, so those are these offsets, minus 25 and plus 10. So we know, we know what this function is like. If you plug in 25 for x naught, and you plug in negative 10 for x1 here, then you get 0, right? So we know what the minimum is. It should converge to 25, negative 10. Kind of nice when you construct the example when you know the answer. See if you get that answer at the end. But in general, when we have complicated things, we aren't going to know what the minimum's going to be, right? Okay, so then I create a gradient descent instance, and I give it my f1, I give it my x, I give it an x naught. I put in negative 50 plus 40 because I knew that that wasn't going to be close to the minimum, and I put in a threshold of 10 to the minus 8. And I just call the descend method on it. And it plots out, and I wish that I had time to squeeze this a little bit, but the idea here is that it gives me xk at each of these iterations. So this is the second iteration because x naught is negative 50 plus 40. So then the very next step, it got to negative 43, negative 15. The next step, negative 38, negative 10. This negative 10 here, that's where we know our minimum is going to be in x2. So that's already there. And see that after that, it doesn't, it pretty much sticks right there at negative 10. It doesn't really go too far away from it. It jumps a little there. And then the other variable is what's getting minimized throughout here. So negative 38, we're going to positive 25 here, right? Negative 33, positive 25, and then it's pretty much there. I'm truncating this to 3 digits or 4 digits, so it doesn't show too much. It also shows the gradients. It also shows the delta x's, delta g's, and then it also has alpha column, but it's off the page. Now let's lambdify the function f1 so we can plot. So we lambdify f1, and we unpack the xk values. So what I'm going to do is I'm going to show each step where we were in the plane, and then I initialize x f1. I want to evaluate x f1 at each of these f1 values, or each of these values. So I do that. I then plot a contour plot, which I could have brought the f1 lambdas together, but anyway, it's a little bit inefficient. But open this up. I do a contour plot. And I also do the gradient descent scatter plot, and I connect the dots. And what we see is this. So it's this big sort of like stretched out bowl shape. And we started out at negative 50, positive 40. So we started out here. And the coloring of this line is going from white to red. So as we get closer to the end, so we start out here. The next point was here. The next point was here, here, and then we pretty much jump very, very close to our minimum. And that's right where we thought we were going to be. So it worked quite well. Okay. Now consider f2. So I can define my f2 using a little definition here. using the array and matrix SymPy functionality, and it allows me to do dot products, and I just do them. And then I do gradient descent on F2. I started out at the same point, or no, 50, negative 40. I started off at a different point, positive 50, negative 40, just for fun. And we descend again, and the minimum of this turns out to be 0, 0, 0, and we approach that. We get quite close to it. So we'll plot this one as well in pretty much the same way that we plotted the other one. And we see that we started out here, it jumped pretty close. It only took a few steps really to get pretty close. And then it just sort of iterates around in there, tries to get closer. So that is, kind of see it gets wild in there. So, yeah. So that's gradient descent. I know that some of you guys at least have taken Dr. Einstein's class on optimization.
Oh, Dane also did, like previous session, right?
Yeah.
But will this method work for the nonlinear function also, or just linear?
It can work for nonlinear as well. Yeah. So it works on. It is not guaranteed to work though. So there are some guarantees that you can state that are that depend on linearity, depend on convexity too. So this method, I believe the one, I think maybe both of these methods, if you can solve in the classical case for the alpha values. And in the other case, I think it's guaranteed always. If you have a linear convex function, you're guaranteed to find the global minimum or converge to the global minimum. But there are, even for nonlinear functions, it could still work. It's just you're not guaranteed that it'll work. And if it's not a convex function, then you're not guaranteed it's a global minimum. You might find a minimum, but yeah.
For this method, we haven't talked about the constraint of that function.
Yeah, so there are no constraints in this. This is called unconstrained optimization. So I'm hoping that by Wednesday I can get a lecture together with to do some linear programming and consider constraints. But that's a very good point. This has no constraints on any of the variables, so it'll just go off and do whatever. And you are there are others. Did you guys do conjugate gradient descent? Is that what you guys did? Conjugate gradient method?
Did what was described was the gradient descent method. I didn't know what is
Which version of it is?
Version of it.
Yeah.
But we use only one function, fmin_con mostly, and then
in MATLAB?
Yeah, we build this objective function and constraint function, and then plug it in.
Yeah. Nice. Yeah, I mean so you're kind of seeing like how you would start to build those types of things.
Mm-hmm.
It's a type of numerical method, and in this class we're trying to stay away from numerics for the most part, just because that's the next class is on numerics. But when you get into optimization, you're pretty much going to get into numerical methods. So it's worthwhile seeing these, even if it's we're not focused on the numerics right now. But the iterative techniques are very useful. I could have kept it less numerical if I'd stuck to the classical method, but it's just not very useful. So, yeah. So this is one way to minimize something, and there are others. And if you have constraints, then you have to take a little bit different approach. Although a lot of methods still will use gradient, like the gradient as a pointer toward where you want to go, and so it's important. That's part of why you'll often see gradient descent first, is to get a kind of an idea of how a lot of these other ones are going to go. So, but I showed you guys one that is actually pretty useful. This version was a nice innovation in '88 and is still usable and applicable. So the algorithms it generates are pretty solid. Yeah. Okay. So with if there are no other questions, Your Honor, we'll conclude.